Hi everyone. So today I just want to do something nice and simple, which is actually figure out some basic facts about observing the Andromeda galaxy. So the Andromeda galaxy is our closest nearby kind of substantial galaxy. It's one that's pretty much in the same size as the Milky Way. It's about 10 to the 11 solar masses worth of stars. And it's also another disky galaxy. I think the Andromeda galaxy is a little larger. Anyway, so it's about 700, 800 megaparsecs away, and it's about the same size as the Milky Way. And apparently, that means that it is possible to see with the naked eye. And so, what I want to do today is just kind of calculate how big it is going to look like on the sky, and how bright it should be. Okay, so let me first draw kind of a general picture of what the Andromeda galaxy is going to look like. So the Andromeda galaxy, it's a disk. It's got a kind of a bulge. This disk has spiral arms. And I think when you actually look at it in the sky, I believe it's actually face on. So by that I mean that you can see the spiral arms. So that's why it's very beautiful. One of the reasons it's very beautiful. Besides the fact that, it's the easiest spiral galaxy to see. So from end to end, so the radius of this guy is about 20 kiloparsecs. And just so you guys know what a parsec is, 1 parsec is about 3 light years. And so let's calculate how far that is in meters, let's say. So a light year is how far light travels in a year, which is 3 times 10 to the 8 meters per second. And 1 year has 3 times 10 to the 7 seconds, approximately. So this is about 15 plus 1, which is 10 to the 16 meters. So this is 1 light year. Or I guess if you want to divide by 3, it's 10 to the 13 kilometers. So that is 10 trillion kilometers. So pretty far. A light year is pretty far. A parsec is 3 times a light year, and a kiloparsec is going to be 3,000 times a light year. So it's about equal to 3 times 10 to the 16 kilometers. So that's 1 kiloparsec. Yeah, so that just gives you an approximate idea of how big these things are. So anyway, so I guess I should give you a number, right? So from one side to the other, I think it's about 100,000 light years. Is 1 kiloparsec. Sorry, 20 kiloparsecs from one side to the other. So the total diameter is going to be 40 kiloparsecs. That's going to be about 100,000 light years. And 100,000 years is about the whole of human history, so it's kind of a long time. Actually, something that I think is pretty funny is people always think that if you look, there's so many stars in the galaxy, why have we not seen aliens yet? Well, one reason is because the galaxy is huge and it takes forever for light to travel to us. So if there was another life form that evolved at kind of the exact same time as humans, you'd be able to see, essentially no stars. You wouldn't be able to see them because even if they had the technology, you'd have to wait for so long before you could even see it. Of course, they could have evolved earlier, and that's, I think, normally what people look for. But anyway, so that's kind of a moot point. The point is, Andromeda is about 20 kiloparsecs in radius, or 40 kiloparsecs across, and the distance to Andromeda is measured to be about 800 kiloparsecs. And so what that means is if you are looking at Andromeda from here, its angular size, the angular theta, is going to be such that this distance is 40, this distance is 800, so theta in radians is equal to 40 over 800, which is 4 over 80, which is 1 over 20, or about equal to 0.05. And now to get that in degrees, let's multiply 1 over 20 times 180 over pi. So that's 90 over pi, which is about 30. I think I did something wrong here. I feel like it should be much smaller than that. Sorry, this is 3, not not 30. That's what I did wrong. Okay, so I'm going to erase that. So it's going to be about 3 degrees. 30 degrees on the sky is absolutely gigantic, by the way, which is why I hesitated before saying that. So let's see. Okay, so it's going to be about 3 degrees on the sky, and just to give you a frame of reference, when you look up at the sky and you size, so it's kind of Andromeda kind of extends 6 times the length of the sun, the size of the sun, or the full moon. The full moon is about also the same size as the sun in the sky. So, so it's about 6 times. So imagine like stacking 6 full moons next to each other. That's actually how far across Andromeda extends. And kind of another way that you can think of it is if you hold out your arm, and stick out your thumb, and use that to cover up the sun or the moon, it'll roughly cover it up. So your thumbnail is about the size of half a degree. So stack 6 thumbnails next to each other, and that is the size of the Andromeda galaxy. In practice, I believe it is smaller than that. You can probably only see about 1/10 of this. So yeah, because the only part which you're going to be able to see of the galaxy is kind of this dense inner region around the bulge. This stuff you can probably see with a reasonably small telescope. So actually, at some point I want to go out and do that. But yeah, so Andromeda itself is pretty big, about 3 degrees across. So that's cool. And the other question you might want to know is how bright it is. And so I'm going to do just a simple calculation. And we're going to do it in terms of magnitudes, because that way you're able to compare it to other stars. So what a magnitude is it's a unit that was used traditionally. So maybe let me erase this and kind of explain what magnitudes are. So what a magnitude is it's a traditional way, which is actually still in use today, to measure how bright something is. And the way it was, I think, invented in ancient Greece, and the way they did it is they picked, one of the brightest stars in the sky. It was Vega, I believe. And they said, okay, let's call that magnitude 0. And then the star that's about half as bright we'll call magnitude 1. And the star that's about half as bright as that we call magnitude 2. I don't know if it's half, but it's something like that. And then went down. And so the kind of the brightest thing that you can see with your human eye is about magnitude 6. And that's if you have really good eyesight. I think probably me, because my eyes suck, I probably could only see like a magnitude 5 star. And that's 100 times, a magnitude 5 star is 100 times dimmer than a magnitude 0 star. The actual formula for the magnitude is, it's all defined in terms of a relative scale, and the difference between the magnitudes is equal to, so if you have 2 stars, or galaxies, or anything really, of 2 different magnitudes, you can calculate, and you measure their fluxes, which is how much energy you receive from them per unit time, per unit area. The difference in their magnitudes is going to correspond to negative 2.5 times log base 10 of the ratio between their fluxes. And so fluxes in general are equal to luminosity, or proportional to luminosity over distance squared. So in this case, then, we can write m1 minus m2 is equal to minus 2.5 log 10 of L1 over L2 times d1 squared and d2 squared on top. Right. And so by rules of logs, you can expand this out, and then so you also will get this is equal to negative 2.5 log, I'm going to drop the 10, L1 over L2, and then I'm going to do like 3 things at once. First, I'm going to separate this from that, and so add a log 10, and then I'm going to, this is d2 over d1 squared, so I'm going to move that outside, so we'll have a minus 5 log d2 over d1, and then I'll flip the d2 over d1 and take the minus sign out. So this will become a 5 log d1 over d2. And so what we're going to do is we're going to utilize some information that we know about the sun. So we're going to kind of find the magnitude of Andromeda using some basic facts about the sun. So the sun has a luminosity unit called L sun, and its distance is at 1 AU, But actually, kind of maybe easier is I know that the absolute magnitude of the sun, which is if the sun was at 10 parsecs, then sun, this is not mass, this is magnitude, is equal to 4.8. Or I'll just say 5, because those numbers are the same thing. So this is the sun. Andromeda, as we see, it has about 10 to the 10 to the 11 stars. So I'm just going to assume that each star has a solar luminosity, which is actually not a bad assumption, I believe, and say the Andromeda luminosity is 10 to the 11 solar luminosities. And its distance is equal to 800 kiloparsecs. So let's solve for this. So let's call M2 the sun. M1 is then equal to negative 2.5 log of 10 to the 11 L sun over L sun, so this is just log of 10 to the 11, plus 5 log 800 over, so 800,000 over 10, so that's 80,000. And just, I'm going to round that up to 100,000. Just for simplicity's sake. Okay, so we're going to have minus 2.5 times 11 plus 5 times 5. And so what is this going to be equal to? You can actually kind of already see, but I'm just going to pull up a calculator. So, so let me drag this onto the screen. So if I have a calculator, I have 25 minus 2.5 times 11. Okay, so that didn't work because it does not do order of operations. So let me do minus 2.5 times 11, and then I'll add 25. And so this is minus 2.5. So I must have done something wrong, because by that argument, it should be like one of the brightest things in the sky. Oh yeah. But the problem is that it's spread over a large region, so you actually kind of have to take apart these 10 to the 12 solar masses and spread it apart across over the whole region that Andromeda takes up. So if it's 3 degrees on a side and you view it face on, then you have a 3 degree by 3 degree square, in which all of this flux is coming out of. So you actually have to normalize for that. Yeah, maybe I should do that. So let's say that I'm actually not 100% sure what the right way to think about this is. But the upshot is, this should be spread out over that region, and so that's why this is really large. So this, if you had a star that was magnitude 2.5, it would be by far the brightest thing in the sky. The brightest star in the sky that we know of is I believe the star Sirius, and that's mostly because it's only a few parsecs away, and that has had magnitude 0. It's not the most luminous star, but it's the brightest star because it's close to us. Yeah, so actually, this is a little not promising, because I would really like to know what how bright Andromeda is if I were to go out and look at it in the sky. So let's do some approximations. Let's figure out what the angular resolution of your eye is, and just for argument's sake, I'm going to say I delta theta is equal to 1 arc minute, which is 1/60th of a degree, which is about 1 over 3600 of a radian. Yeah, because you multiply by pi over 180, which is about 1 over 60. So that's the angular ability of your eye. And so let's just say then, if we take all of this flux, this 10 to the 11 solar luminosities, and spread it out over this much angular distance, and then we look in one patch over here that is of this size squared, right? What does that correspond to? What magnitude would that correspond to? And so this is, let's see. So this is an arc minute. Yeah, I'll do it with an arc minute. So normally the unit that they use is magnitudes per square arc second, which is basically you do this process that I'm doing right now, but instead of 1 arc minute, which is a 60th of a degree, you use an arc second, which is 1 over 3600th of a degree, and therefore you multiply this by 60 to get the radians. But we'll do this because I think this is about the angular resolution of your eye. I might be off by a factor of 10 in either direction, but like mostly in the larger direction. But I think this is like a lower bound on it. Okay, so let's see. Okay, so I have 10 to the 12 solar masses, and it's divided across this distance. Let's see. So I'm going to erase some stuff so I can figure out how to think about this. I'm going to erase all this. This is just the definition of that. This is a picture of Andromeda. We don't need that. We do need this distance, but we don't need that. We don't need that anymore. We might need it in a second, actually, but yeah. And I already have that written again down here, so I'll erase this and start writing up here. Okay, so I basically have 9 square degrees, 3 by 3, over which Andromeda is spread. I think it's a little less than that, but let's just do this for argument's sake. And what I want to do is figure out if I take Andromeda and stick it in here, you know, all of this luminosity is evenly spread out throughout this region, and I look in this section over here, what is the magnitude going to be? So what that means is I have 10 to the 11 L sun, and this is the luminosity, and I divide that by d squared, which is 800 kiloparsecs squared, and what that does is it gives me the flux at the Earth. Right. And then in order to get the flux at the Earth per square arc minute, I need to divide this then by 3 degrees times 60 arc minutes per degree and square that. So this is going to give me then 10 to the 11 L sun over 64,000 kiloparsecs squared, and then 1 over, so this becomes 180 squared, so 18 times, let's say 200 squared, right? So 4, 2, 3, 4, arc square arc minute. Maybe an easier way to do this is just say the actual flux that I care about is the amount that is in here, right? So this is an easier way to do it. So if I take 1 square arc minute and I divide it by 3 times 60 squared times 60 arc minutes squared, and then I multiply this by 10 to the 11 L sun, this is equal to the flux coming from that region, right? And so what I need to do then is effectively take this 10 to the 11 that I had over here and just divide it by 180 squared. And so I'm going to, so 180 squared is equal to so let me just do 18 times 18 because we kind of want to just know that. 14, 8, 1, so 624. 624. Okay. So I'm going to round this down to 50,000. And the reason is because Andromeda is not quite a square. It's kind of 3 degrees the long way, but probably maybe half as that. So I'm just going to round down. And so this then becomes 10 to the 11 divided by 5 times 10 to the 4. Right? So if we stick in a 5 times 10 to the 4 over here. Oops. Okay, great. Sorry about that. So if you stick in a 5 times 10 to the 4, okay, then this becomes over 5 times 10 to the 4. So this becomes, this is still plus 25, right? This is the same. And we're subtracting 2.5 times log of, so that's 7, 5 times 10 to the 6. So I'm going to now again pull out this handy dandy calculator and turn it into scientific, just because I just want to get this number kind of more exactly. 5 times 1, 2, 3, 4, 5, 6, so that's a million. So it's 5 million, I could have done that. And we log 10 it. Here it is. So that's 6.7. Okay, 6.7 times 2.5 is equal to 16.75. So it's equal to minus 16.75. And now if you subtract 25 minus 16.75, that is equal to 8.25. Okay, so this is a little more like it. Equals 8.25. And if you recall, you can probably only see things from magnitude 1 all the way down to magnitude 6, which means that theoretically if Andromeda was evenly spread throughout this whole area, it probably would be a little too dim to see with the naked eye. In practice, however, it's like very dense at the center, so if you recall the picture I drew, here's the bulge and here's kind of the disk, and it kind of bulges out like that maybe. In practice, what you'll be able to see is this bulge area, because that's way more dense than the rest of it. So you'll actually be able to see it with your naked eye, and it should actually probably be pretty dim then. But if it's like 10 times brighter, that'll be up by 2.5 magnitudes, which puts it at 6. It just puts it at the edge of what you're able to see. So you should see it at about magnitude 5. So it should be comparable to really the dimmest stars in the sky, and it should be spread, I think it's probably about 1/10 of a degree. So what is that, 6 arc minutes or something, across the sky. So it's actually it should be a pretty sizable blob that you see, and it will be kind of fuzzy. So you can actually see this with your naked eye, and probably even more of it with a telescope. Okay, great. So that took a little longer than I thought, but I hope that was interesting. And tomorrow I'll talk about magnetohydrodynamics.